The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, so the second speaker is Dr. Hu. He's an assistant professor in the concrete industry management program in Texas State University at San Marcos, and he received his PhD in geotechnical and materials engineering from Iowa State University in 2005. He is teaching construction and concrete related courses, including construction materials and concrete construction methods, management of concrete products and concrete problems. Dr. Hu is a member of American Concrete Institute Commission Committees 130 and Sustainability of Concrete 237, Self-Consolidating Concrete 238, and definitely the 555. We'll be ready now.
Thanks for the very nice introduction. So this topic is talking about recycled lead-based paint, contaminate deconstruction masonry materials as aggregate for Portland cement concrete. So it's a very unique topic. Later on I'll show you some pictures and prove that why this is unique. So before I start this one, well, I was actually invited to talk in a section related to sustainability in the ASCE summit in Dallas last month. So before I walk in the room, I have no idea, and that section was hosted by the committee in bituminous material. So actually I walked into the wrong room. So I'm glad I'm coming to ACI and talk to people that do concrete. So Anyway, those guys are very friendly, so I'm glad they did not kill me in that section. So, okay, the research was actually was done back in our state when I was doing postdoc over there, and Dr. Jiong was the PI of that project, who's sitting right here. So, okay, go ahead to start. So, why we need to do this? Okay. So, well, the reason we do this, I don't know how many of you are familiar with lead-based paint, but it was used before 1970s in many of different kind of buildings, especially in military buildings, just because those kind of paint provide better quality. But of course, we know that lead is not a good thing, so you don't really want to deal with that. So after 1970s, a lot of those, well, the paint is not allowed to use, but we have those old buildings need to be demolished. And the problem is how do we deal with that? So there are different kind of practice for you to deal with that, but none of that is really cost effective. So we are trying to figure out whether there's any better way to deal with this. So the objective of this research is to figure out, say, whether there's any way, any effective method, both cost effective and environmentally effective, for deconstruct masonry material to be used in concrete. Another thing is whether we can effectively sequence the lead in concrete, because that's a key thing. We don't want those lead to go out. Yes, we'll be using that as aggregate in concrete, but the key thing is try to keep the lead inside. So one other thing is to develop a rational mixed design method, but proportional this kind of aggregate to be used for new concrete. So those are the three major objectives of this research. Approach. So the idea is actually fairly simple. So we want to use the high pH environment of concrete. So if you look at this chart, and you can see that the lead leachability really depends on the pH. And for those of you familiar with concrete, our pH is right here. So that actually tells you the leachability of lead is really low. Because based on the classification, it is not just the total lead in a material that counts. More importantly, it's a leachable lead. So how much lead can get out from a material. That's what it counts. So that's the main idea, is to use a high pH of concrete to try to keep the lead inside a new concrete. So the scope of this presentation, we talk about a few different kind of things. First thing is how do we simulate the lead-based paint contaminate masonry material for us to use? Another thing is the characterize the recycled aggregate, and of course we'll talk about fresh and hardened concrete property made with those recycled lead-based paint contaminate material. Then a little, I'm going to talk a little bit about the mix design. We developed some nomograph for you for the purpose of this mix design, and cost analyze to see if these things really cost effective. Okay, the first stage is to simulate lead-based paint contaminated materials for deconstruction. So originally we were planning to get some material from a real demolished structure, but it turned out that either we don't have anything really nearby, so it's not really cost effective to get anything. So we decided we're going to make our own. So luckily we find a lab that's not really used, so we do most of those things in that lab because we are dealing with lab. No one really liked that. So a few things. First things, we identified four different kind of masonry material. Two of them are CMU concrete masonry, and another two are clay bricks over there. So, and we're trying to get lead-based paint. So the next thing is to make our own lead-based paint. So if any of you want to use that, we might still have some. So, so basically what we do, we do have one of the co-PI in the project, Mr. Jiong, who is our lab manager in our environmental lab. So he's familiar with this. So we use certain mixed proportions to make our own lead-based paint. So basically we use this ball mill to mix all the ingredients together and for 24 hours before we get this lead-based paint. So the next stage is really taking quite a lot of time. So it was like about 2 months of work to paint all this. So it's a long process. So as myself with one other undergraduate student, we spent literally two months over there just paint. And you can see we all dressed up for that. So the next stage is, of course, when you want to use for concrete, you need to crush that. So we use a jaw crusher with an opening about 3/4 inch, crush all these bricks and to get a proper size for concrete purpose. So one major concern we have is during this demolishment, what kind of contamination you're dealing with. So it's not directly related to concrete, but we want to know exactly how much lead we are dealing with. So we did a few things. The first thing is to check we monitor the lead concentration during the crushing. Basically, that's a crusher over there, and we identify 6 different locations from close, like 24 inch, to up to several feet apart from the crusher to see how much lead you have on the ground. So as you can expect it, the closer you have, the more lead you have. So one other thing we do is to check out the airborne lead. So that was also something people have concern on, is how much lead you're going to take in if you're not wearing a mask. So, and during the crush process of about 3 hours, we have these sensors. This is actually a small pump to take all the airs in, and we find out the lead in that 3-hour operation with about 1,000 pounds of crushing, the lead concentration about 24 micrograms per kilometer. So by OSHA, it's actually okay, 50, because that's a limit. But as we all know, that 0 is the best. So actually, one other thing we do is both myself and the student work with me, we did blood tests before and after. I think we did 3 times just to check out whether we have any lead in our body. So luckily, there's not much change. So, okay, here's our final product. We got 4 different kind of masonry. So Of course, they're all different. Absorption mostly are very high, as expected. Another thing is that when we use concrete masonry, the material we get is actually in better shape compared to clay brick. Most of clay brick, especially those bigger particles, because they're brittle, so they are irregular shape, so might not be that good for concrete use. And if you see the next few slides, we're talking about gradation, they have more coarser particles. But in this study, in order to simplify this study, we use 100% of all this. So we did not use any natural aggregate to replace. We use 100% recycled aggregate instead of combined with natural aggregate, just to simplify this research. One other thing I want to point out is that the recycled lead-based paint contaminated masonry material we have, it do shows that it's higher than the TCLP lead requirement. That's 5 microgram per liter. I'll explain a little bit later on that. So gradation, we have 2 of that is based on our DOT gradation that we usually use for concrete. And you can see that all the 4 masonry material we have, they have slightly higher or much higher percentage of coarser aggregates. So again, it might not be 100% appropriate for concrete use, but to simplify this research, we use 100% that. Voids in aggregate, as you can expect, we do the uncompact void content. Clay brick, because their shape, they have a higher void content compared to concrete masonry unit. We use 3 different kinds of cements here. Portland cement type 1, and we use CSA cement, and another one is a combination of Portland cement with 5% of phosphate. We are trying to see if phosphate can be more effective if you add it into cement. Okay, so that's why I say this is unique. So when you're mixing concrete in a concrete lab, dressing like this, yes, you're different. So we actually do a lot of precautions over here. There's a big vacuum over here trying to take most of the dust out during mixing, and we also set up a lot of traffic cones to surrounding areas, close the lab so that no one else get in, and also wash the lab shortly after the mixing. But again, well, when other guys see us doing this work there, well, they say, hey, these guys are doing some high-end work over there, but in fact, we are just trying to protect ourselves. Another thing I want to mention is that during mixing, well, unfortunately, we do this all in summer. So literally, you lose a couple pounds after mixing. What we do is that we use 4 different kinds of aggregates, 3 different kinds of cements, 3 different aggregate to cement ratios, 3.0, 4.5, and 6, 4 and 3 different workability levels, 1 to 3 inch, 3 to 4 inch, 6 to 7 inch, just to see if we can produce concrete with different workability. And there are a total of over 50 concrete mixes produced in this research. Okay, fresh concrete properties. Again, there were 3 different slump range that we use. Anyone see there's a mistake over here? I was intent to change this, but for some reason it's keep going there. So this two is supposed to be flipped. So we do have 3 different range of slump that we produce. Basically, what we do is to change water cement ratio to obtain different slump value. That's hardened concrete. Well, all these things we go through standards, curing, strength tests, and one thing I do want to point out is that on all the breaking samples, you see that a lot of those breaking surfaces are on those painted surface. That's expected because the surfaces are smooth. But still, most of our strengths are quite reasonable, and we can get as high as 6,000 psi. TCLP, that's the toxicity correlation of leaching procedures. So basically, again, as I point out, it is not the total lead content matter. It is how much lead it will leach out. So basically, it's a chemical process to check out how much lead it will be leaching throughout the mixture. So by the regulations higher than 5 microgram per liter, they will consider as hazard material. So this is a summary of the results. Strengths, as you can expect it, when you increase the cement factor, your strength will increase. Water-cement ratio, again, as expected, we have 4 different masonry units, but they all show very clear trend that increase of water-cement ratio, your strength will decrease. And we have a wide range of strengths over here from close to 7,000 psi to as low as 1,000 psi. That, of course, is depend on your cement content and aggregate content and water-cement ratio. So a general trend you can see is, as what I point out, another thing is the concrete made with masonry B and D had higher strength compared to A and C. That might just because of the different composition and different shape we have on those aggregate. Another thing, as we point out, the most important thing is to see whether this is safe. So based on the results from TCLP test, as you can see, except the 4 points with masonry D that we use, that is the clay brick, all of them has TCLP lower than 5 microgram per liter. That means they're all safe based on the requirement, lower than 5 microgram per liter. Another thing we check out is to see if aggregate to cement ratio have anything related to total lead, but this is really not very clear trend we observe from our study. So we did a statistic analysis based on the data. We obtained a few things I want to point out. First of all, we did try to add, we did use calcium sulfur aluminum cement, CSA cement, to see how much difference it's going to make. Results show that there's really not that much impact on leachability, but we do get higher early strength compared to type 1 cement. Another thing is about adding 5% of phosphate in normal Portland cement, and with this 5% addition, there's really not much significant change on TCLP leachability. So that shows that, well, 2 things. If you want to add more, it's possible, but however, it might not be cost effective at that point. Okay, one other thing we did is based on different type of aggregate we use, because we use different aggregate to cement ratio, different cement content, different water cement ratio. We're trying to figure out if we can provide some guideline with this specific aggregate, whether what kind of things you can follow for a mixed design. I don't know how many of you are familiar with the Nomograph for mixed design, but a quick review is that you follow these 3 laws. Basically, strengths relate to water cement ratio. Strengths decrease when water cement ratio increase. And another thing is water cement ratio versus aggregate cement ratio. When the water cement ratio increase or aggregate cement ratio increase, they are related if you have the same slump. Another thing is aggregate cement ratio versus cement content. Of course, when you increase aggregate cement ratio, your cement content decrease. So how you can use this, basically, if you want to design for different strengths. Say, for example, if this shows that 6,000 psi, you go right, maybe with this line, you go down, you determine your water cement ratio. After that, you go further down, depending on the slump, you can determine your aggregate cement ratio, and further left, you determine your cement content. So basically, you get a key component of your mixed design. Another way you can use is if you design concrete for different workability. You can go this with different slumps. You can determine different water cement ratio, different cement content. So basically, you can use this kind of nomograph to help you to design concrete. So let's see with our own data what we have. So these are the 2 with CMU as aggregates. So as you can see that they follow the trend pretty well. So with increase of water cement ratio, the strength, and this is with the different slump, and this is cement factor. So basically, again, if you're with the aggregate you use, what you can do in order to design, say, 4,000 psi in 7 days, you can determine your water cement ratio, then your aggregate cement ratio and cement content. So that's how do you use these nomographs. All the 4 different kind of masonry materials, we have very similar results. Of course, that little different compared to each other, but the trend are pretty much the same. We also do the same thing for CSA cement and type 1 cement with 5% of phosphate, but on that we only have one range of slump value instead of 3 lines over here, comparing to type 1 cement. Okay. One other major benefit for this research, in addition to figure out whether technically it's feasible, we want to check out how much environmental benefit you're going to get. So traditionally, when you deal with lead-based paint, you have a few options. First option, well, you leave the building over there, but usually that's not an option. But the option you can have is demolish it, and based on your state regulation, you can dump it at a normal landfill, or in some state, which has strict requirement, you have to dump it in a secure landfill. That could be very costly. One other option is you use sandblast or different kind of practice to remove the surface paint. And you dump it in some secure landfill. The remaining, you can consider that as a normal masonry material. Either reuse that or dump it regular landfill. So, well, of course, obviously this practice we are proposing, we can minimize this kind of negative impact because you can use this back into new concrete without any additional lead-based paint removal process. So those are the main benefit you get out of this. One other thing we did is to check out the cost effectiveness of this. So these are some normal, these are cost information for normal practice of lead-based paint removal. As I say that one typical process is to remove lead-based paint before you demolish a building. So you can see, depending on a different practice, you can have from $5 per square feet up to $12 per square feet. Different kind of practice. Average is about 9. So that actually tells you a good amount of money will need to be spent if you follow this practice. Now, in order to do this cost analysis, our approach is we kind of make up 3 dummy buildings, different sizes, floor areas from 300 square feet to up to 96,000 square feet, and lead-based paint contaminate wall space differently from 13 to 104,000 square feet. And compare these are the 3 different buildings. We also provide 3 scenarios comparing to what our practice is to demolish it directly and reuse it in concrete. So scenario 1 is to depose it in a construction waste landfill. That's a regular landfill. Another scenario 2 is depose in a secure hazard material landfill. Again, that's very costly. Scenario number 3 is to remove lead-based paint, then depose in a construction waste landfill. So we compare our practice, which is directly demolish the whole structure and reuse it back to concrete to see how much money we can save. So these are the results. So basically, as you can see, that with the with the decrease of the size of a building, that actually tell you relatively you have more wall areas in that building for lead-based paint. So with results actually shows that if you have a smaller building like this, your cost saving can be higher. Well, another thing I want to point out is there's 3 different scenarios. Once again, scenario 1 is to just simply demolish it and put it in regular landfill. And you can see the saving could be, it's really hard to see from this 3D, but about $6 per square feet to as low as $1 per square feet. But that's the first scenario. But scenario 2, which is much tougher because you have to dump it in a secure landfill, our saving could be up to like $30 per square feet in a smaller size of building comparing, and a normal building, big size of building could be like $10 per square feet. That's quite a lot of saving. And scenario 3 is to remove the surface lead-based paint, and then the remaining of them put it into landfill. And you can see the saving could be close to $45 per square feet. So all the 4 we're showing all the 4 different kind of aggregates here used. Again, these are our major findings over here. So this research actually proved that, first of all, technically it's feasible because you can make concrete with acceptable strength and slump. Environmentally, it's feasible because you can effectively make this contaminated material, the lead, keep this lead in your new concrete, and cost effectively also. So major conclusions. So we first of all accept the 4 mixes with clay brick as masonry materials. Most of the mix have the TCLP lower than 5 microgram per liter. That means it's environmentally safe. Recycle those aggregates we use will not be considered as hazard under the RCRA, that's Resource Conservation and Recovering Act. Desirable workability and strength of concrete can be achieved by appropriate mix design. Of course, we can optimize this by combining this with natural aggregate. Again, this was not in the scope of that research. The method of mix design, those Nomograph we develop can be used to design concrete based on the specific aggregate that you use. Cost effectiveness, we can save between from like $8 per square feet to $45 per square feet based on different scenarios and different cases. The cost saving can result from eliminate L-based paint removal and waste material deposit could be very beneficial. So this research was sponsored by CERDEP from DOD, and it was research with, again, I finished this research back in our state. So we have a few documentations related to this, so if any of you are interested, there are more details showing there. With that, I would like to conclude this presentation.